With today's highly redundant networks, it's quite possible that packets that belong to the same flow may be routed over different paths. Now, what constitutes packets in the same flow? Well, packets that are part of the same flow will be coming from the same source IP, going to the same destination IP, using the same source and destination port numbers. They'll have the same quality of service markings. They'll also be arriving inbound on the exact same interface of a router. So all of those packets are part of the same flow. However, it's quite possible that they're going to take a completely different path through the network, especially if we're doing load balancing. So if we examine traffic coming from this PC, let's say the traffic went this way. And we're using TCP right now. And let's say a packet that's part of the exact same flow decides to go this way through our load balancing that we have set up. So this is packet number 1, this is packet number 2. If we're using TCP, is it a problem if packet 2 arrives before packet 1? No, it's not. Why? Because of TCP's sequence numbers. Every single one of those TCP segments are sequenced. As a result, the end station has the ability to put that information back together in the correct order so it makes sense. However, what if we're using UDP? If we're using UDP, could it be an issue if our packet number 2 arrives before packet number 1? Well, does UDP have any sequencing numbers at all? No, it doesn't. It does not sequence those segments. So out of order data could become an issue for UDP. So it's important that we have the ability to analyze this particular issue. So for example, if we're experiencing some problems with end stations that are using UDP, we might want to double check to see what paths are being used for that UDP traffic. And we might have to modify the flow of that traffic and make sure that all the UDP segments, all those UDP, therefore the packets, are taking the exact same path through the network. Where with TCP, it's not a big deal.